The summer of 2025 was supposed to be routine. Across the globe, arrays of telescopes, their lenses pointed at the deep black, performed their endless silent ballet, mapping the predictable clockwork of the heavens. Then they caught a ghost, a faint smear of light moving at a velocity that immediately set alarm bells ringing in observatory control rooms. 153,000 miles per hour. An object on a trajectory so extreme, so hyperbolic, it could only mean one thing. This was not from here. It was an intruder from the interstellar dark, only the third such visitor ever confirmed. They catalogued it with a dry, technical designation, 3 Atlas. The official announcements were calm, reassuring. An interstellar comet, they said. A spectacular visitor, a pristine chunk of ice and rock from another star, swinging around our sun before vanishing forever back into the void. A scientific bonanza, not a threat. For a few weeks, the world marveled at the headlines and went back to sleep. But in the background, the data started to tell a different story. A whisper, then a murmur, then a chorus of confusion rising from the astronomy forums and closed research channels. The numbers didn't add up. The behavior defied easy classification. What if, from the very first moment, we had looked at 3 Atlas and seen only what we wanted to see? What if our comforting models of harmless, icy wanderers were blinding us to a far more unsettling reality? While the public slept, other events began to cascade, each strange in its own right, yet together forming a pattern that raised the hair on the back of the neck. Japan issued a historic megaquake warning, its seismological networks buzzing with a tension that veteran experts found unnerving. Across the globe, major internet backbones experienced synchronized fleeting failures that engineers could only diagnose as impossible. The sun, as if in response to some unseen provocateur, erupted with a series of X-class flares of unexpected violence from a region that hadn't been on the radar for such fury. And in the most chilling theoretical circles, orbital simulations began to spit out results that made veteran astrophysicists lean back from their screens in silence. Some models suggested Mercury, the innermost planet, had already begun a subtle, fatal dance out of its ancient rhythm. Stay with me, because what we are about to piece together, by connecting the dots between the official data and the whispered anomalies, suggests a timeline no one is prepared for. It suggests that Earth, our home, may have an expiration date set not by our own hands, but by a cosmic passerby. The clock, according to this synthesis, started ticking months ago. We have 50 years. Before we go further, if you're as captivated by these cosmic puzzles as I am, go ahead and hit that like button right now. It helps more than you know. Subscribe and hit the notification bell to stay absolutely connected as we track this story across its full, shocking breadth. This is a deep, multi-part investigation. I want to hear from you too. Leave a comment down below, telling me where in the world you're watching from, what hour it is in your corner of the planet, and whether you think the full, unfiltered picture of what 3 Atlas represents is being shared with the public. Your perspective is part of this story. Now, let's rewind to the beginning. Part 1. The gravitational wrecking ball arrives. In the summer of 2025, the automated Sky Survey telescopes pinged. An object, high velocity, unbound orbit. The calculations were run and rerun. The trajectory was unambiguous, a hyperbolic arc, the mathematical signature of an object not tied to our sun's gravity. It was a free traveler, a rogue. It was given the name 3 Atlas, a formal tag marking it as the 3rd interstellar object ever confirmed. The scientific press releases were swift and designed to inspire wonder, not fear. A comet from another star, a chance to study the chemistry of another solar system. It would pass safely, they emphasized, at a distance of 1.8 astronomical units from Earth. That's nearly twice the distance from the Earth to the Sun. No danger. Case closed. But in the months that followed, as every major telescope on Earth and in space turned to scrutinize this gift from the galaxy, the initial narrative began to fray at the edges. The data was odd. First, there was the issue of its core. Estimates of the nucleus size ranged wildly, from a modest 440 meters to a staggering 5.6 kilometers across. That disparity alone was a red flag. It suggested we weren't seeing a solid, defined body clearly. Then came the polarimetry studies. When scientists measured how sunlight scattered off 3 Atlas's surface and coma, they got a pattern that made no sense: a deep and narrow negative polarization branch. This wasn't just unusual, it was unprecedented. No known comet or asteroid in our solar system had ever produced such a signature. It was as if the physical texture of this thing was alien, literally. Then the chemistry readings came in from spectrometers. They revealed the expected components of a comet: water ice, carbon dioxide, dust, but in strange ratios, with carbon dioxide dominating. And there were other lines in the spectral data, hints of something more: metal, substantial metal content. One preprint paper cautiously described 3 Atlas as a primitive metal-rich interstellar body. That is not the profile of a simple dirty snowball from the frozen outskirts of a star system. That is the profile of something that formed in a different neighborhood, under different, perhaps more violent conditions. These anomalies cracked open a door in the scientific mind, a door that led away from the comfortable and into the realm of disturbing possibilities. The mainstream view held firm. It was a comet, exhibiting some unusual properties because it was forged around another star. But a small, growing chorus began to ask a different question. What if we are being fooled by appearances? What if the coma and the tail, the classic features of a comet, are just a mask? What if, beneath that veil of outgassing ice, 3 Atlas is something far denser, far more massive? Not exotic matter from science fiction, but simply a compact, heavy body whose true mass is hidden by its deceptive brightness. Consider the implications of mass. Gravity is the silent architect of the cosmos. A comet's gravity is negligible, but a dense object, even a few kilometers across, if it carried the density of iron or some even more compact material, would have a gravitational signature orders of magnitude greater. Gravitational force weakens with distance, but it never disappears. A sufficiently massive object swinging through the inner solar system would act like a stone thrown into a still pond. The ripples would spread. Our solar system is an ancient, delicate balance. The planets orbit in resonances that have persisted for billions of years. Jupiter's immense gravity acts as a shield, but also a puppeteer. The moon stabilizes Earth's tilt, giving us stable seasons. This entire architecture is a web of subtle, persistent tugs. Introduce a new strong gravitational source, a wrecking ball on a hyperbolic trajectory, and you introduce chaos. Not immediate, apocalyptic chaos, but a subtle, patient kind. A nudge to a planet's velocity of a few centimeters per second is meaningless today. But over hundreds of orbits, over decades, that nudge compounds. Orbits can stretch, resonances can break. The stability we take for eternal can begin to unwind. This is the core of the wrecking ball hypothesis. It posits that 3 Atlas is not a spectator, but an actor. Its passage may have delivered imperceptible gravitational nudges to Mercury, Venus, Earth, and Mars. The effects would be tiny, buried in the noise of current measurements. But gravity is patient, and orbital mechanics is a game of compounding interest. The true consequences of today's tiny perturbation might not reveal themselves for 50 years or 100. The object is receding now, a fading dot headed back into the interstellar gloom at tremendous speed. Official astronomy has largely moved on, but if the wrecking ball hypothesis contains even a grain of truth, then the departure of 3 Atlas is not the end of the story. It is merely the end of the prologue. The gravitational ripples it left in its wake are still propagating through the fabric of our solar system. We may be living in the calm before a storm that takes centuries to brew, a storm that begins with the quiet, inexorable alteration of a planet's path. But this gravitational mystery is only the first thread. In the parts ahead, we will pull on others. We will examine the historic megaquake warning in Japan that coincided with 3 Atlas's perihelion. We will dissect the global internet glitches that some network engineers swear defy conventional explanation. We will look at the solar flares that erupted from a seemingly placid sun. And we will scrutinize the orbital simulations that predict, with cold digital certainty, catastrophic changes in the coming decades. Each event, in isolation, can be explained away. Coincidence, normal geological process, software bugs, standard solar activity. But when they cluster in the temporal shadow of the first interstellar object ever found to exhibit such profound anomalies, a single, unsettling question becomes unavoidable. What if 3 Atlas was not just passing through? What if it was a trigger? The scientists continue their observations. The data streams in. The debates in journals are polite, measured, but at the edges, a few researchers wonder if we are missing the forest for the trees. They wonder if our models, built for the familiar objects of our own solar system, are inadequate to capture the full terrifying reality of this visitor. They wonder if we should be looking at our world with new anxious eyes. Because if the wrecking ball has already swung, the impact is still to come. The official story was a comfort, a blanket of known physics thrown over the unknown. 3 Atlas was a comet. It had a coma, a tail. It outgassed volatiles when heated by the sun. Every indicator, said the press releases from the world's leading space agencies, pointed to a slightly unusual but fundamentally familiar icy body. They had the spectra to prove it. They had the imagery. The closest approach to Earth was a clean 1.8 astronomical units, a vast and safe distance. The gravitational influence at that range from an object with a comet's minuscule mass would be less than a whisper. It would not register on the most sensitive instruments on Earth. No danger. The case was not just closed, it was sealed with the stamp of consensus. But consensus is not the same as truth, and in science, it is the anomalies that point the way, the data points that stubbornly refuse to fit the curve. For 3 Atlas, those anomalies were not just refusing to fit, they were plotting a curve of their own, one that led into a dark and unexplored space of possibility. Let's dismantle the comet assumption piece by piece, starting with the most profound mystery, the polarization data. When light strikes a surface, it scatters. By measuring the polarization of that scattered light, the orientation of its waves, scientists can infer incredible detail about the texture, composition, and structure of that surface. For decades, astronomers have built a catalogue of polarization signatures. Rocky asteroids produce one pattern, icy comets produce another, dust clouds produce a third. When the team pointed their polarimeter at 3 Atlas, they expected to see something within that known family of curves. What they saw was nothing from their catalogue. The object exhibited what is called a deep and narrow negative polarization branch. In simpler terms, the way light bounced off it was alien. It didn't match the rough, porous surface of a typical comet nucleus. It didn't match the smooth metallic sheen of an asteroid. It matched nothing. One researcher, in a private forum later leaked, described it as the scattering profile of ground-up gemstones or highly structured metallic foam. It was a fingerprint that belonged to no suspect in the database. This alone should have been a 5-alarm fire in the world of planetary science. Instead, it was buried in the third paragraph of a technical paper, an intriguing oddity for future study. Then came the mass estimates, or more accurately, the profound uncertainty surrounding them. Determining the mass of a distant object is notoriously tricky. You can estimate it from brightness if you know the reflectivity, but that's a guess. You can try to measure its gravitational influence on other objects, but for something this small and distant, that's impossible. For 3 Atlas, scientists relied on the outgassing. As the sun heated the nucleus, jets of gas and dust erupted, acting like tiny thrusters. By measuring the acceleration these jets imparted to the nucleus, a phenomenon called non-gravitational acceleration, they could backtrack to estimate the mass. The numbers that came back were all over the map, implying a nucleus size from a few hundred meters to several kilometers. But the non-gravitational acceleration itself was subtle, weirdly subtle, for an object with such a pronounced coma. It was as if the outgassing was a superficial effect, a fizz on the surface of something much more substantial and inert. The calculated density, based on the brighter end of the size estimates, was laughably low, suggesting a porous snowflake. Based on the larger, darker size estimates, the density climbed into the realm of solid rock or even metal. The data allowed for both a light, fluffy comet and a dense, heavy bullet. The mainstream adopted the former. The wrecking ball hypothesis considered the latter. This is where the chemistry added its disturbing voice. Spectroscopy breaks light into rainbows, and within those rainbows are dark and bright lines, the chemical barcodes of the universe. The spectra of 3 Atlas confirmed the presence of volatile ices, carbon dioxide, carbon monoxide, water. But the ratios were wrong. In our solar system, comets from the Oort cloud are dominated by water ice. 3 Atlas was dominated by carbon dioxide. This suggests it formed in a much colder region of its home system, a place where CO2 could freeze out. But more intriguing were the faint, stubborn lines that indicated the presence of metals, not just trace metals locked in silicates, but potentially native metals, iron, nickel. One paper suggested the body could be carbonaceous but metal-rich, a combination that is incredibly rare and points to a violent history. A simple, icy planetesimal forming in the cold dark doesn't concentrate metal. A shattered core of a protoplanet, or a body that underwent intense, star-blasting heat does. The primitive, metal-rich interstellar body tag was a dry, academic way of saying, this thing is built from different stuff and it's been through something. Combine these anomalies, the alien light scattering, the ambiguous but potentially high mass, the strange metal-bearing chemistry, and the solid, icy comet model begins to look like a suit of clothes on a figure that doesn't fit. The wrecking ball hypothesis proposes a different figure inside those clothes. Imagine an object that is not a homogeneous mix of ice and dust. Imagine instead a dense, metallic core. Perhaps it's the iron heart of a shattered dwarf planet, a fragment of a cosmic catastrophe that happened billions of years ago around another star. This core, over eons adrift in the interstellar void, accretes a mantle of frozen gases and dust, the detritus of the galaxy. It becomes a kind of cosmic onion. When it streaks into our inner solar system and nears the sun, the outer layers, the icy mantle, heat up. They sublimate, they fizz and erupt, creating the beautiful coma and the spectacular tail. They make it look for all the world like a comet. But underneath that spectacular display, the heavy, dense core remains, largely unaffected, its true mass hidden behind the veil of its own evaporation. If this is true, then everything changes, especially the gravity. Let's run the numbers with terrifying generosity. Assume 3 Atlas has a nucleus 5 kilometers across, at the upper end of estimates. If it's a standard comet density, say 0.5 grams per cubic centimeter, like a compacted snowdrift, its mass is about 10^14 kilograms, 100 billion tons. That's a lot, but gravitationally, at 1.8 AU, it's a mosquito landing on a tank. Its pull on Earth is billions of times weaker than the Moon's. Now keep the size the same, but change the composition. Make it have the density of iron, 8 grams per cubic centimeter. Suddenly its mass is 16 times greater. Make it an exotic, ultra-dense material, something that survived from the heart of a supernova. The numbers climb into the realm of the terrifying. At a high, but not impossible density, the mass could be 1,000 times greater than the standard comet estimate. The gravitational influence scales directly with mass. That mosquito becomes a sparrow, then a hawk. The tidal forces, the difference in its pull on the near side of Earth versus the far side, while still tiny, become measurable. They become a potential trigger. A trigger for what? This is where the hypothesis moves from the object itself to the solar system it passed through. The inner planets are a finely tuned, if chaotic, clock. Mercury's orbit is already eccentric, precessing. Venus and Earth are locked in a resonant dance. Mars is influenced by the asteroid belt and the Titan, Jupiter. The system is stable over billions of years, but it is not inflexible. It is a web under tension. Introduce a new mass, even a modest one on a hyperbolic trajectory, and you pluck that web. The pluck creates vibrations. In orbital mechanics, these vibrations are tiny changes in velocity in orbital parameters, semi-major axis, eccentricity, inclination. The changes are minuscule, meters per second, fractions of a degree, parts per billion in distance, inhumanly small. But the solar system has time, gravity compounds. A meter per second nudge today means a kilometer of positional difference in a year. Over decades, that kilometer becomes thousands, then millions. Over centuries, the accumulated perturbation can resonate with the natural frequencies of other planets' orbits. Energy can be transferred. Jupiter, the gravitational giant, can amplify small kicks into large shoves. The most vulnerable planet is Mercury. It's small, close to the Sun, and its orbit is already the most chaotic. Simulations of solar system stability show that over billions of years, Mercury has a small but non-zero chance of going rogue, either falling into the Sun or colliding with Venus. These simulations require no external influence. The chaos is innate. But an external influence, a gravitational kick from a passing massive body, could act as a catalyst. It could advance that timeline from billions of years to millennia, or even centuries. By giving Mercury a slight, specific nudge at its perihelion, you could dramatically accelerate the precession of its orbit, increasing the chances of a close encounter with Venus. The fallout from that would cascade outward, a gravitational domino effect reaching Earth. For Earth, the direct gravitational pull from 3 Atlas was negligible, even under the most extreme secret mass scenario. But the indirect effects are the true danger. If Mercury is destabilized, the entire gravitational budget of the inner solar system is recalculated. Earth's own orbit could become more elliptical over time. Our distance from the Sun would vary more between summer and winter. More critically, Earth's axial tilt, stabilized by the Moon, could experience new, subtle torques from the changing orbits of Venus and Jupiter. A change of just 1 degree in tilt shifts climate belts by hundreds of miles. Agriculture, built on millennia of stable seasons, would fail at continental scales. A change of 5 degrees is an ice age scenario. The proponents of the wrecking ball hypothesis do not claim this is certain. They claim it is possible, given the anomalous data. They accuse the mainstream of clinging to the Comet model not because it fits all the data, but because it is the only model that allows everyone to sleep at night. The other model, the dense core interloper, opens a door to a future of silent, creeping catastrophe. It suggests that the most significant event in human history might have already happened, and we celebrated it as a scientific curiosity. It suggests that the changes have already been seeded, that the equations are already in motion, and that we are now in the long, slow fall before the impact. The object is gone, but its shadow in this hypothesis is just now beginning to stretch across the future. This idea that a passerby could rewrite the destiny of a solar system is so profound it feels like myth. It touches a deep, archaic fear of celestial omens and portents. But this is not astrology. It is orbital mechanics played with frightening parameters. It turns 3 Atlas from a visitor into a bullet, and our solar system into a target. But a bullet needs a fingerprint, a mark of its passage. If 3 Atlas was this massive, shouldn't it have left other signs beyond theoretical orbital perturbations? Shouldn't the Earth itself have trembled? As we will see in the next part, according to some, it did. At the very moment 3 Atlas was at its closest point to the Sun, Japan's seismic networks lit up with a warning that shook the nation to its core. The megaquake advisory was issued, and a whisper began. The visitor didn't just shake the heavens, it shook the Earth. The ground beneath Japan is a prisoner of geology. The Philippine sea plate, a vast slab of the Earth's crust, is slowly, relentlessly diving beneath the Eurasian plate. This subduction zone, the Nankai Trough, runs like a scar along the country's southern coast. It is a place of immense, accumulating strain. The plates do not slide smoothly, they stick. Stress builds over decades, over centuries, until the rock can hold no more and fails catastrophically. The resulting megaquake, the event of magnitude 9.0 or higher, is not a matter of if, but when. Japan lives with this certainty. Its culture, its infrastructure, its very psyche is shaped by it. So when the Japan Meteorological Agency issued a historic megaquake advisory in the latter part of 2025, it was not crying wolf. It was the official, sober voice of a nation acknowledging that the seismic wolves were at the door and the lock was straining. The advisory was specific and terrifying. It cited a dramatic increase in seismic activity along the Nankai Trough, a proliferation of small tremors and slow slip events, silent, undetectable motions deep underground that suggested the main fault zone was entering a critical phase. Coastal communities reviewed tsunami evacuation routes. Emergency supplies vanished from shelves. The nation held its breath. Mainstream seismology had a clear, internally consistent explanation: plate tectonics. The strain had been building since the last great rupture in the 1940s. The fault was simply reaching its natural breaking point. The timing, while alarming, was within statistical expectation. The story should have ended there, in the grim but familiar territory of geological inevitability. But the universe has a tendency to weave coincidence into narrative, and the timing of this advisory was exquisitely precise. It fell within the same narrow window that 3 Atlas, the interstellar visitor, was making its closest approach to the Sun and, consequently, its closest pass to Earth's orbital neighborhood. In the data-rich echo chambers of specialized geology and astronomy forums, a connection was proposed. It was a whisper at first, then a thread of discussion. What if the quake warning wasn't just a terrestrial phenomenon? What if the final, minuscule increment of stress that pushed the Nankai Trough from loaded to critical came not from below, but from above? The proposed mechanism is tidal forcing, a concept as elegant as it is unsettling. We are familiar with ocean tides, the rhythmic rise and fall of the sea pulled by the moon and sun. Less known are earth tides. The solid ground beneath our feet is not perfectly rigid. It is an elastic sphere. The gravitational pull of the Moon and Sun actually stretches and compresses the planet itself, causing the ground to rise and fall by tens of centimeters twice a day. This motion is measurable with sensitive instruments. Crucially, these tidal forces add and subtract tiny amounts of stress on fault lines. It is a well-documented, though subtle phenomenon that the timing of some earthquakes correlates with the peaks of earth tides. The tide provides the final push on a fault already poised to fail. Now, scale the idea up. Replace the Moon with a closer or more massive object. The tidal force scales with the mass of the perturbing body and inversely with the cube of the distance. This means distance is fantastically important. Double the distance and the tidal force falls by a factor of 8. The Moon is 384,000 kilometers away. 3 Atlas, at its closest, was over 270 million kilometers away, more than 700 times farther. For 3 Atlas to produce a tidal force on Earth, even 1,000th as strong as the Moon's, it would need to be unimaginably massive. We are talking about an object with a significant fraction of Earth's own mass. This is the first and greatest hurdle for the hypothesis. The proponents, however, point back to the wrecking ball model. What if 3 Atlas was that massive, its true weight hidden inside its cometary disguise? If it were, then during its closest approach, its gravitational field would have created a distinct, if localized, tidal bulge on Earth. This bulge would have traveled across the planet's surface as Earth rotated. For a few hours, the strain field along the Nankai Trough would have been subtly altered. If the fault was in a state of critical sensitivity, where any small addition could trigger a rupture, this cosmic tide could have been the proverbial straw. The idea is seductive in its narrative simplicity. A mysterious object from deep space flies by, and days later, one of the most seismically volatile regions on Earth stirs with ominous warning. It connects the cosmic to the terrestrial, satisfying a deep human desire for a unified, dramatic story. It transforms a random tectonic event into a chapter in a larger epic. But science is not conducted by narrative satisfaction. It is conducted by data, and here, the data offers a brutal rebuttal. Japan, perhaps more than any nation, is a web of precision measurement. Its GeoNet array of GPS stations blankets the islands, monitoring ground deformation with millimeter accuracy. These instruments measure the Earth tides from the Moon and Sun with exquisite precision. They detect the slow, relentless strain buildup from subduction. If a tidal force from 3 Atlas, large enough to meaningfully stress a fault, had swept across Japan, these GPS networks would have seen it. The ground would have shown a clear, anomalous deformation pattern, a wave of stretching and compression correlating exactly with the object's trajectory. No such signal was found. The crust behaved exactly as predicted by the standard model of lunar-solar tides and tectonic strain. The silence of the GPS data is deafening. Let's engage in a thought experiment with generous, even outrageous parameters. Assume 3 Atlas had the density of a white dwarf star fragment, an impossibly dense object. Assume it passed at its known distance. Even then, the math shows the resulting tidal stress on Earth's crust would be measured in pascals, mere micropascals. The tectonic stress in a subduction zone like the Nankai Trough is measured in megapascals, millions of times greater. The cosmic contribution would be like adding a single grain of sand to a loaded dump truck and expecting it to break the axle. The physics simply doesn't support the mechanism. Furthermore, the Earth is bombarded by gravitational influences constantly. Planets align. The Moon's orbit varies. These produce tidal forces orders of magnitude greater than anything 3 Atlas could have produced, even under the most exotic assumptions. If such forces routinely triggered megaquakes, our planet would be in a state of perpetual shuddering. They do not. The reason is that earthquake triggering requires not just a force, but a fault that is ready to go. The tidal force can only advance or delay the inevitable by a tiny amount. It cannot create the immense stored energy of a megaquake that comes only from centuries of plate motion. So why does the theory persist in the shadowy corners of the internet? The answer lies in psychology, not seismology. A megaquake caused by plate tectonics is a tragedy, but a local one. It is a consequence of the Earth's living, shifting geology. A megaquake triggered by an interstellar object is a cosmic event. It makes humanity part of a grand, terrifying galactic story. It appeals to our sense of significance, even if that significance is catastrophic. It also provides a seductive answer to the agonizing unpredictability of earthquakes. Our science can tell us where and how big, but it cannot tell us when. That uncertainty is a vacuum, and nature abhors a vacuum. The human mind rushes to fill it with patterns, with causes. 3 Atlas, mysterious and timely, becomes a perfect candidate, a celestial scapegoat for our terrestrial fears. The mainstream geophysical community sees no connection. The gravitational effects are too weak by many orders of magnitude, the distance too vast, the observational evidence non-existent. The megaquake advisory was a somber acknowledgement of the Earth's own powerful internal dynamics. The danger was always here, grinding away beneath the Japanese islands, waiting for its moment. It needed no assistance from the stars. Yet, as the seismic warning faded from headlines, another series of anomalies surfaced, this time not in the ground, but in the very fabric of our global civilization. In the days surrounding 3 Atlas's perihelion, the internet, that shimmering, supposedly resilient web of human connection, experienced a series of glitches that those who maintain its core found deeply, professionally unnerving. And some of them would point their fingers not at faulty code, but at the fabric of space-time itself, warped by a passing, hidden mass. The modern world runs on synchronized time, not approximate time, not clock-on-the-wall time, but nanosecond precise, globally coordinated time. Every financial transaction, every data packet routed across the internet, every cell phone call, every GPS fix depends on countless servers agreeing on what time it is, down to fractions of a millisecond. This synchronization is maintained by the Network Time Protocol, NTP, which cascades time from a hierarchy of sources at the top of which sit atomic clocks. These are not metaphors. They are devices that measure the vibration of atoms, so stable they might lose or gain less than a second over the entire age of the universe. They are the silent, flawless heartbeat of the digital age. In a span of just 48 hours, during the peak of 3 Atlas's solar passage, that heartbeat stuttered. It was not a global blackout, but a series of synchronized fleeting failures that rippled through the backbone of the internet. Major cloud service providers in North America, Asia, and Europe reported brief, unexplained outages. Financial trading platforms stuttered, causing million-dollar flash anomalies. Streaming services hiccuped. The official explanations, when they came, were the standard lexicon of tech apology. A routing table misconfiguration, an erroneous software update, cascading failures in a data center cluster. To the public, it was a minor inconvenience. To the network engineers who managed the core infrastructure, the time servers, the root DNS servers, the major exchange points, it was something else. It felt wrong. In the private channels where these engineers communicate, a different story began to form, built not on speculation, but on server logs. They reported microdrifts in atomic clock synchronization. NTP servers, which should have been in perfect agreement, suddenly disagreed by several milliseconds. For atomic clocks, this is an eternity. It is an impossibility under normal operation. A millisecond drift is what you might see from a cheap quartz watch over a month, not from a cesium fountain clock over an hour. These drifts were brief, self-correcting, but they were recorded. More strangely, they seem to correlate, very roughly, with the position of 3 Atlas relative to Earth. As the object moved through a specific sector of space, clocks in one hemisphere would very subtly lag behind clocks in another. Then, as it passed, they would resynchronize. The theory that emerged from these technical trenches was breathtaking in its implications. It had nothing to do with software or hardware. It was rooted in Einstein's general theory of relativity. Massive objects warp space-time. One consequence of this warping is gravitational time dilation. Time runs slower in a stronger gravitational field. This is not science fiction, it is engineering reality. The GPS satellites in orbit around Earth have to correct for this effect, because time runs faster for them in Earth's weaker gravity well than it does for receivers on the ground. If they didn't, GPS would be inaccurate by kilometers within a day. The engineers' whispered hypothesis was this: what if 3 Atlas was not just somewhat massive, but massively massive? What if its gravitational field was strong enough that, as it passed Earth, it created a localized gradient in space-time curvature? An atomic clock on the side of Earth momentarily closer to the object would be in a very slightly stronger gravitational potential than a clock on the far side. One would tick imperceptibly, slower than the other. For the exquisitely synchronized protocols of the internet, this fractional difference, a few milliseconds over thousands of kilometers, would be catastrophic. Secure connections, TLS, SSL, would fail because timestamps in digital certificates wouldn't match. Data packets would arrive out of order, confusing routing algorithms. The entire delicate dance of global communication, which assumes a uniform flow of time, would briefly stumble. The idea is intellectually seductive. It explains a software problem with fundamental physics. It elevates a network glitch to a cosmic event. It suggests we detected the visitor not just with telescopes, but with the entire infrastructure of our civilization, which momentarily acted as a planet-sized gravity wave detector. But does the physics hold up? Let's be brutally quantitative. The strength of gravitational time dilation depends on the gravitational potential. At Earth's surface, we are deep in the Sun's gravity well, which causes time to run about 1 part in a billion, slower than in deep space. To produce a millisecond-scale time difference between 2 locations on Earth over a few hours, you would need a gravitational gradient far steeper than the Sun provides at our orbit. You would need a source of immense mass passing very close. 3 Atlas passed at 1.8 astronomical units. At that distance, even an object with the mass of Earth itself would produce a gravitational time dilation effect on our planet that is utterly negligible, trillions of times smaller than the effect of Earth's own gravity on its surface clocks. To create the millisecond drifts described, 3 Atlas would need to be not just planet mass, but star mass. We are talking about something with the mass of Jupiter, or more. An object of that mass passing within the inner solar system would not be a subtle visitor. It would be the dominant gravitational player. Its pull would yank asteroids from their orbits, perturb the paths of every spacecraft, visibly distort the orbits of Mars and Venus. It would be glaringly, obviously massive. Its cometary coma would be irrelevant. We would be tracking it by its gravitational wake alone. No such perturbations were observed. The orbits of known asteroids, the trajectories of interplanetary probes, all remained within predicted bounds. Furthermore, the energy required to warp space-time enough to cause those clock drifts is astronomical. That much mass energy cannot be hidden. It would reveal itself through gravitational lensing, bending the light from background stars in an obvious way. Every major telescope on Earth would have seen it. They did not. 3 Atlas appeared as a point of light, not a lens. So, what really happened in those 48 hours? The mundane, probabilistic truth is almost certainly more boring, and more complex than relativity. The internet is not a single machine. It is an unimaginably complex organic mess of interconnected systems running on billions of lines of code. Software updates are deployed constantly. Configuration files are edited. Hardware fails. These events are uncorrelated, happening thousands of times an hour across the globe. Usually the system's redundancy absorbs them, but occasionally, through sheer bad luck, multiple small failures align. A buggy routing update in one continent propagates. A faulty memory module in a key data center fails at the same time. A solar radio burst, a real space weather event that happened around that time, interferes with satellite timing signals. These uncorrelated failures can create a brief, synchronized seeming global event. It's the digital equivalent of a perfect storm. The human mind, however, rejects perfect storms. We crave narrative, a single cause. A mysterious interstellar object provides a magnificent single cause. It turns a random, chaotic failure of our own complex creation into a signpost from the cosmos. It makes us feel like we are living inside a significant story, rather than victims of our own fragile, overcomplicated technology. The engineers who proposed the time dilation theory are not foolish. They are experts swimming in a sea of complexity, and they grasped for a beautiful, simple answer that explained the inexplicable in their logs. But beauty and truth are not always companions. The gravitational time dilation theory, while physically implausible, reveals a profound shift in our relationship with the cosmos. We have built a world so precise, so interconnected, that it might, in theory, tremble at the passage of a distant star. Our networks have become canaries in the cosmic coal mine, sensitive to influences we are only beginning to imagine. Even if 3 Atlas was not the cause, the fact that we can imagine it as a cause and build a semi-plausible physics argument around it shows how far our awareness has expanded. We are no longer just looking at the stars. We are listening with our machines for their faintest echoes. But if our digital world was subtly glitching, what of the great power source at the center of our system? As 3 Atlas reached its perihelion, its closest point to the Sun, our star itself seemed to wake in fury. From a seemingly placid surface, a series of violent eruptions tore into space, of an intensity that surprised even veteran solar physicists. And once again, the question was asked, was the Sun merely following its own rhythms, or was it responding to a gravitational pluck from a passing stranger? The Sun is a roiling ball of plasma, a thermonuclear furnace where complexity births violence. Its surface is not solid, but a seething convective layer from which magnetic fields erupt like twisted ropes. Where these fields punch through, they suppress the boiling plasma, creating cooler, darker patches we call sunspots. These sunspots are not benign. The magnetic fields are strained, storing titanic energy like wound springs. When the fields suddenly reconfigure, a process called magnetic reconnection, that energy is released in an instant. We call this a solar flare. The largest, X-class flares, can release energy equivalent to 1 billion hydrogen bombs, hurling radiation and charged particles across the solar system at near light speed. Often, they are accompanied by coronal mass ejections, CMEs, billion-ton clouds of magnetized plasma that can trigger geomagnetic storms on Earth. Solar activity follows a rough 11-year cycle, from quiet, solar minimum, to stormy, solar maximum. 2025 was a year of rising activity, climbing toward a predicted maximum. Solar physicists expected flares. But in the weeks surrounding 3 Atlas's perihelion, the Sun did more than just follow the script. A massive active region, designated AR4294, blossomed on its face. It grew complex, its magnetic topology becoming a tangled knot of stored energy. And then it erupted, not once, but repeatedly, A series of powerful X-class flares tore from its heart, followed by fast, Earth-directed CMEs. The space weather forecasts, usually cautious, upgraded to severe storm warnings. Satellites were put into safe mode. Airlines rerouted polar flights to avoid radiation exposure. The aurora borealis danced as far south as California and Italy. It was a spectacular, potentially damaging, but ultimately natural event. Yet the timing, again, was conspicuous. The most intense cluster of flares occurred within a window centered on 3 Atlas's closest approach to the Sun. To the pattern-seeking mind, a connection seemed to pulse with possibility. A new fringe theory emerged, one that attempted to link the interstellar visitor to the solar tantrum. The argument moved beyond simple gravity and into the realm of magnetohydrodynamics, the physics of magnetized fluids. The Sun's influence does not stop at its visible surface. It blows a constant stream of charged particles, the solar wind, that carves out a vast bubble in interstellar space called the heliosphere. Embedded within this expanding wind is the Sun's magnetic field, stretched and twisted by solar rotation into a structure like a spinning ballerina's skirt. At the heart of this structure is the heliospheric current sheet, a wavy, warped surface where the Sun's magnetic field changes polarity. It's a fundamental part of the Sun's extended magnetic architecture. The theory proposed that 3 Atlas, as a massive body, could interact with this architecture not through direct contact, but through its gravity. As it passed through the inner heliosphere, its gravitational field would perturb the tenuous plasma of the solar wind. Imagine dropping a heavy stone into a slow-moving river. The stone creates ripples, disturbances in the flow. In this case, the ripples would be Alfvén waves, disturbances that travel along magnetic field lines. These waves, the theory suggested, could propagate back along the solar wind, all the way to the Sun itself. Upon reaching the Sun's surface, these waves could deliver a kind of jolt to already stressed magnetic regions, like AR 4294, providing the final nudge needed to trigger reconnection and a flare. In this view, 3 Atlas didn't create the flare's energy. It merely provided the tap that released energy the Sun had already stored. It is a sophisticated idea, connecting a distant object to stellar activity through subtle plasma physics. It has the feel of cutting-edge, systems-level thinking. But does it survive a confrontation with scale and energy? The answer, once more, lies in the brutal dominance of the Sun's own power. First, consider the scales. The heliosphere extends over 100 astronomical units. The current sheet is a diffuse, massive structure. 3 Atlas, even under the most generous mass estimates, is a tiny speck plowing through an ocean. The gravitational wake it creates in the near vacuum of the solar wind would be infinitesimally small, confined to a region maybe a few times its own size. For that minuscule disturbance to coherently propagate back across tens of millions of kilometers, maintaining enough integrity to affect a specific, stressed region on the Sun is akin to expecting the ripples from a pebble dropped in the Pacific Ocean to trigger a specific geyser in Yellowstone. The waves would dissipate, be overwhelmed by the turbulent solar wind, and vanish into noise long before reaching the Sun. Second, and decisively, is the energy budget. A major X-class flare releases around 10 to 26 joules of energy. This energy is stored in the magnetic fields of the active region, which are generated by dynamo processes inside the Sun, driven by its own rotation and convection. The amount of gravitational or kinetic energy 3 Atlas could impart to the solar wind is many, many orders of magnitude smaller. It is the difference between lighting a match and detuning a nuclear bomb. The match cannot trigger the bomb unless the bomb's mechanism is already primed to the point of absurd instability. The Sun's active regions are not that unstable. They flare when their internal magnetic complexity reaches a natural breaking point. There is also a powerful historical counterargument: sun-grazing comets. We have observed comets from our own solar system, like those in the Kreutz family, plunge directly into the sun's corona through regions of intense magnetic field and dense plasma. They are much closer and dive through much more sensitive regions of the sun's atmosphere than 3 Atlas ever did. If a comet passage could trigger flares, we would see a clear correlation. We do not. These comets vaporize silently, without eliciting so much as a sputter from the sun's magnetic activity. The sun flares according to its own internal sovereign rhythm. So why does the connection persist? Beyond simple coincidence, it speaks to a desire to see the cosmos as an interconnected whole, where everything affects everything else. It feels more meaningful, more alive, than a universe where a passerby ignores the star it passes, and the star ignores it. We anthropomorphize the sun, imagining it responding to an intrusion. Furthermore, solar physics, while advanced, still cannot predict the exact timing of major flares. That predictive gap leaves room for alternative explanations. 3 Atlas neatly fills that gap for the events of 2025. The mainstream solar physics view is unambiguous. AR 42294 flared because its magnetic fields became complex and unstable. The sun was in an active phase of its cycle. The intensity, while notable, fell within the statistical distribution of what such a large active region can produce. 3 Atlas was a spectator. Its passage was a coincidence, a story we superimpose on the much grander, more powerful story of stellar magnetism. But if the sun was indifferent, and the Earth's crust unresponsive, and the internet merely buggy, where does the true danger of the wrecking ball hypothesis lie? It must lie in the one place where gravity patience and persistence have no counterbalance. In the void itself, in the slow-motion ballet of orbits. This is where the most chilling evidence for the hypothesis emerged, not from telescopes or seismometers, but from the digital wilderness of simulation. This is where we saw in cold, calculated detail how a solar system can die. Somewhere in the unregulated digital wilderness of online astronomy forums, buried in threads with cryptic titles and populated by usernames that were strings of numbers and shadows, a simulation appeared. It wasn't hosted on a university server or linked from a reputable journal. It was a zipped file, a package of code and data, uploaded to a file-sharing service with an anonymous tag. The person who posted it claimed no official affiliation, only a deep familiarity with orbital dynamics software, the same professional-grade tools used by NASA's Jet Propulsion Laboratory to navigate probes across the solar system and predict asteroid trajectories centuries into the future. The post was simple: a set of initial conditions, a description of the modified parameters, and a warning. The simulation was not a prediction, the author insisted. It was a sensitivity analysis, a what-if scenario. But the results, once the clock was run forward, were so viscerally terrifying that they immediately transcended their speculative origins. They became a prophecy in the eyes of those who saw them. The radical assumption at the heart of the simulation was a single number: the mass of 3 Atlas. The simulator discarded the official estimates derived from outgassing and brightness. Instead, they treated the object as ultra-dense. They gave it a density not of ice or rock, but of something like osmium or iridium, the densest naturally occurring elements. Or they invoked speculative materials like degenerate matter, the stuff of white dwarf stars. In this model, 3 Atlas packed 10, 100, perhaps 1,000 times more mass into its estimated volume than any normal comet should. It transformed the visitor from a snowy wanderer into a compact bullet of astonishing heft. With this one change loaded into the system, the simulation began. It integrated the equations of motion forward in time, calculating the gravitational pull of every major body: the sun, the planets, the large asteroids, and now this new, monstrously dense point of mass on its hyperbolic trajectory. The initial results were subtle. As 3 Atlas swung through the inner solar system, its powerful gravity tugged on the planets. Not with the force of a collision, but with the delicate, persistent pull of a magnet passing near a pile of iron filings. Mercury, Venus, Earth, and Mars each experienced a perturbation, a tiny change in their velocity vectors measured in mere centimeters per second. In the short term, over days or weeks, these changes were meaningless, lost in the noise of normal gravitational interactions. The planets continued on their paths. 3 Atlas receded, its hyperbolic curve carrying it out toward the Oort cloud and beyond, forever. But orbital mechanics is the realm of compound interest. Gravity is patient, and its effects accumulate with ruthless exponential logic. The simulation did not run for weeks, it ran for decades, then centuries, and over that stretched canvas of time, the tiny nudges bestowed by the passing wrecking ball began to blossom into catastrophe. Mercury, the smallest and innermost planet, with the most eccentric and dynamically precarious orbit, was the first to succumb. The extra kick from 3 Atlas amplified the natural chaos of its motion. Its orbital ellipse became more elongated. Its perihelion, its closest point to the Sun, began to precess faster, shifting its closest approach around the solar circumference. Over simulated decades, Mercury's path began to intersect more closely with the orbit of Venus. The 2 planets entered a gravitational dance of increasing intimacy and violence. Every close pass transferred energy, pumping up Mercury's eccentricity further. In some simulation runs, within a mere 50 years, Mercury's orbit became so unstable that it either plunged directly into the Sun, vaporizing in a final, silent flash, or was flung outward on a chaotic path that crossed the asteroid belt, a rogue bullet in the inner system. The fate of Mars was different, but no less terminal. The perturbation from 3 Atlas gave it a slight outward nudge. This minor change altered its delicate gravitational relationship with Jupiter, the solar system's dominant gravitational bully. Resonances developed. Rhythmic gravitational kicks that happened each time Mars and Jupiter lined up in their orbits just so. Over the course of the simulated century, these resonant kicks acted like a steady push, slowly but inexorably driving Mars outward. Its orbit expanded by tens of millions of kilometers. As its average distance from the Sun increased, the solar radiation it received dwindled. The planet's already thin atmosphere, no longer sufficiently warmed, began to freeze out onto the poles in a perpetual thickening frost. Surface temperatures, which could occasionally brush above freezing at the equator, plummeted to a permanent cryogenic deep freeze. The faint hopes for subsurface liquid water vanished. Mars didn't explode or collide, it simply, slowly, froze to death, receding into the darkness as a lifeless, airless tomb. But it was Earth's simulated fate that gripped the heart with true civilization-ending dread. The changes were not explosive, but insidious. The first effect was on Earth's axial tilt. The Moon provides a powerful, stabilizing gyroscopic effect, but the combined gravitational torques from the perturbed orbits of Venus and Jupiter, now subtly altered by the 3 Atlas event, began to exert a new influence. Over decades, Earth's 23.5-degree tilt began to wobble. Not a lot, just a degree or two at first. But a single degree of axial tilt shift moves climate belts by hundreds of miles. The simulation showed this wobble increasing over a century, leading to a new equilibrium tilt several degrees higher. The consequences were immediate and brutal, more extreme seasons. Polar regions would receive blistering summer sun, melting ice caps at an accelerated, unstoppable rate, while their winters would plunge into deeper darkness. The temperate zones that currently support the world's breadbaskets would shift, turning fertile plains into deserts or suffering unpredictable, violent monsoons. The jet streams would become erratic. The climate system upon which global agriculture and human settlement is precariously balanced would be shattered. Simultaneously, Earth's own orbit began to change. Its eccentricity increased. The path around the Sun became more of an oval than a near circle. This meant that for part of the year, Earth would be significantly farther from the Sun, receiving less solar energy. Harsh winters would grow longer and more severe. Growing seasons would shorten unpredictably. The combined feedback of a tilted axis and an elongated orbit created a nightmare scenario. Ice that formed in the longer, colder winters wouldn't fully melt in the shorter, more extreme summers. Reflectivity would increase, cooling the planet further, creating more ice. The simulation showed Earth, within a few centuries, sliding into a rapid onset ice age, a snowball Earth event not seen for hundreds of millions of years. The final, most horrifying outcome of some simulation runs was long-term ejection. As Earth's orbit stretched and its interactions with the now altered giants Jupiter and Saturn changed, the accumulated perturbations crossed a critical threshold. Over centuries, Earth's orbit became so energetic and so elliptical that the Sun's gravity could no longer reliably hold it. In a slow-motion apocalypse, Earth began to drift outward. First, it would become a rogue planet in the outer solar system, a dark world with a frozen, dead surface. Then, over millennia, a close pass from another giant planet, or the gentle tidal pull of the galaxy itself, would give it the final kiss goodbye. Earth would be expelled entirely, cast adrift into the interstellar void, a frozen tomb tumbling forever through the cosmic dark. The clock on this scenario, in the most extreme runs, started at 50 years from the passage of 3 Atlas, 50 years until the unstoppable process began. The simulation was a masterwork of scientific horror. It was detailed, it was visual, it used the legitimate language of orbital dynamics, equations of motion, perturbation theory, resonant angles, n-body integration. It looked and felt authentic, and that is precisely what made it so dangerous and so revealing. Let's step back and examine what this simulation actually represents. It is a thought experiment, and like all thought experiments, its validity is entirely dependent on its initial assumptions. The entire edifice of orbital collapse is built on one foundation, that 3 Atlas possesses an impossible mass. The simulator tried to justify this by invoking exotic matter, or neutronium, the incomprehensibly dense material at the heart of neutron stars. A fragment of neutronium the size of 3 Atlas would indeed have the mass of a small planet. But this is a physical fantasy. Neutronium is only stable under the crushing gravitational pressure found within a neutron star itself. Remove that pressure, and it would explosively decompose in a cataclysm of particle decay. A chunk of it cannot cruise quietly through space, disguised as a comet. The idea violates fundamental nuclear and particle physics. Furthermore, we have direct observational evidence that contradicts the extreme mass assumption. The outgassing behavior, the composition of the coma, the very existence of a tail, all of these are consistent with a modestly massive icy body. To have the mass required to perturb the solar system as shown, 3 Atlas would need to be tens of thousands to millions of times more massive than the observational upper limits allow. Such an object would not have a coma, it would have an atmosphere, it would not be pushed around by solar radiation pressure, it would dominate its local space. Its gravitational influence would have been blatantly obvious in the tracking data of every asteroid and spacecraft in the inner system. None of this was observed. Mainstream orbital dynamicists working at institutions like JPL haven't sounded any alarms because they plug the actual, observationally constrained mass estimates into their models. When they do, the calculated perturbations from 3 Atlas are so minuscule, they vanish into the numerical noise of their simulations. Mercury's orbit remains stable on billion-year timescales. Mars stays put. Earth's axial tilt is locked by the Moon. The solar system, in the professional view, merely shrugged at the passerby. So why does the speculative simulation persist and spread? Because it is terrifying in the most profound way. It provides a narrative of existential threat that is impersonal, cosmic, and utterly unavoidable. It removes human agency and guilt. We are not destroying ourselves through climate change or war. We are victims of a celestial billiard game. There is a strange, dark comfort in that fatalism. It also offers the aesthetic of science, graphs, equations, orbital plots, which grants it a false authority. To the non-specialist, it looks like science and is therefore trusted as science. The human mind is poor at evaluating assumptions, but excellent at responding to visceral, dramatic outcomes. The simulation's persistence speaks less to a scientific truth and more to a deep psychological need. The need for our era to be significant, even if that significance is catastrophic. It is more palatable to believe we are living through the opening act of a solar system-spanning tragedy than to accept that we are witnessing a mildly interesting comet from another star, soon to be forgotten. The Wrecking Ball simulation transforms 3 Atlas from a footnote into an epoch-making event. It gives shape to our amorphous cosmic anxiety, offering a specific, detailed nightmare to replace a general, formless dread. But as we have seen, this nightmare requires physics to break in half. The next question, then, is what if we are wrong about the object's very structure? What if the mass isn't concentrated, but distributed in a way that fools our instruments? This leads us down the final, strangest rabbit hole of all. The hypothesis that 3 Atlas isn't a single thing at all. For centuries, the dirty snowball model of comets has served us well. It's a simple, intuitive picture. A compact nucleus of ice and rock, a few kilometers across, warming as it approaches the sun, shedding gas and dust to form a hazy coma and magnificent tail. This model is embedded in textbooks, in mission planning, in the public imagination. When we look at a comet, we unconsciously see a singular, cohesive body. But what if that fundamental picture is wrong, not just for 3 Atlas, but as a universal concept? What if some of these visitors, especially those from the alien forging grounds of other stars, are assembled differently? This question moves us beyond arguing over the density of a singular nucleus and into the realm of structural possibility. What if the mass of 3 Atlas isn't hidden in a dense core, but is instead spread out, distributed in a configuration that our telescopes and models are inherently bad at seeing? The distributed mass hypothesis didn't spring from nowhere. It germinated from the very anomalies that made 3 Atlas strange from the beginning. Take the polarimetry data, the unprecedented negative polarization branch. Light scattering models for solid surfaces or even loose dust clouds couldn't reproduce it. But what if the light wasn't scattering off a surface at all? What if it was passing through a cloud? Imagine 3 Atlas not as a solid bullet, but as a swarm. A cluster of hundreds or thousands of smaller, boulder-sized or house-sized objects, all traveling together in a loose gravitational association, separated by distances of hundreds of meters or even kilometers. From our vantage point, hundreds of millions of kilometers away, this swarm would appear as a single fuzzy blob, a coma with a bright central condensation. But light passing through such a diffuse, complex structure would scatter in wildly unpredictable ways, potentially creating the bizarre polarization signature that left scientists baffled. We wouldn't be looking at a surface, we'd be looking at a cosmic crowd, and the light would be bouncing between its members in a chaotic dance. Then there's the chemical oddity, metal-rich and carbonaceous. A homogeneous icy body shouldn't be that way, but a heterogeneous swarm could be. Perhaps 3 Atlas is the remnant of a catastrophic collision in another star system, the shrapnel of a protoplanetary smash-up. Some fragments are metallic, chunks of a shattered core. Others are carbon-rich, primitive planetesimals. Others are icy. they all got gravitationally tangled together in the aftermath, forming a flying rubble pile of epic proportions. The sun's heat would preferentially vaporize the ices from the surfaces of all these fragments, creating a unified, mixed coma of gas and dust that shows both metal signatures and carbon molecules, exactly as observed. The nucleus we think we see is just the brightest, densest knot in the swarm. Some theorists go further, blending the dense core and distributed mass ideas. They propose 3 Atlas might be a protoplanetary core fragment surrounded by a swarm of its own debris. A heavy metallic central body, a shattered planet's heart, acts as the gravitational anchor for a cloud of smaller, icy and rocky fragments that were blasted off it in the collision that set it adrift. This scenario offers a way to have both significant mass in the central fragment and the strange observational signatures from the irregular swarm and mixed coma. It's a cosmic onion with a metallic core, a layer of rubble, and an outer veil of outgassing ice. The most speculative fringe of this thinking abandons normal matter entirely. Could the distributed mass include, or even be dominated by, dark matter? We know the universe contains far more dark matter than the ordinary atoms we understand. It interacts gravitationally but not electromagnetically. It doesn't emit, absorb, or scatter light. What if 3 Atlas is a dark comet, a normal icy shard or swarm that has a halo, or core, of dark matter bound to it? This would explain any perceived gravitational excess without a corresponding electromagnetic signature. The object could be more massive than it appears because a portion of its mass is invisible to all our telescopes. It is a chilling idea, suggesting pockets of the universe's greatest mystery could be sailing past our doorstep. But it is also entirely untestable with current technology and remains in the realm of provocative, unfalsifiable speculation. We must ground this in what we actually reliably observed. Recent data from the James Webb Space Telescope and other infrared observatories provided the most definitive composition analysis yet. The coma of 3 Atlas was dominated by carbon dioxide, with substantial carbon monoxide, water ice, and silicate dust. This is, frankly, textbook comet behavior, albeit with an unusual CO2 to H2O ratio. The outgassing rates, the expansion speed of the coma, the morphology of the tail, all of these were successfully modeled by teams assuming a standard, if carbon dioxide-rich, icy nucleus with a mass in the range of billions to trillions of tons. When independent teams fit the same data, they converged on similar mass estimates, all minuscule on a planetary scale. Furthermore, we saw no evidence of fragmentation or a distributed structure. If 3 Atlas were a loose swarm or a rubble pile under extreme stress from the sun's heat and gravity, we would expect to see signs of it spreading out or even disintegrating, especially near perihelion. Famously, Comet Shoemaker Levy 9 was stretched into a string of pearls by Jupiter's gravity before its fatal plunge. 3 Atlas showed nothing of the sort. High-resolution imaging from the Hubble and large ground-based telescopes with adaptive optics showed a single, coherent central condensation. There were no secondary nuclei, no trailed-out fragments. It held itself together like a solid body. The mainstream scientific consensus, therefore, remains firm. 3 Atlas is an interstellar comet. Its unusual properties, the metal hints, the odd polarization, are fascinating puzzles, not paradigm destroyers. The metal content likely indicates it formed in a different region of its home system than our own comets, perhaps closer to its star where metals could condense before being ejected. The polarization anomaly might be due to the unique shape and composition of its dust grains, forged in a different stellar environment and weathered by billions of years of cosmic ray bombardment in interstellar space. These are outstanding scientific questions, the very reason we look at such objects. They enrich our understanding of galactic diversity. They do not require us to invent new physics or panic about hidden mass. So why does the distributed mass hypothesis, with all its subvariants, persist with such vitality? The answer is more human than physical. A normal comet is ultimately mundane. It's a predictable piece of cosmic scenery, a swarm, a shattered planet core, a dark matter bearer. These are mysteries. They speak of violence, of alien formation histories, of the truly unknown. Our minds are magnetically drawn to mystery over mundane explanation. There is also a deep-seated psychological appeal to the idea of a hidden threat. The notion that 3 Atlas conceals its true nature plays directly into primal fears about deception, about dangers that wear a pleasant face. This resonates in a world where trust in surface appearances is increasingly eroded. The hypothesis also thrives in the gaps of our knowledge. We did not land a probe on 3 Atlas. We could not bounce a radar signal off it to directly measure its shape and density. Our knowledge is remote, inferential, based on interpreting faint photons that traveled across millions of kilometers of empty space. That distance inevitably leaves room for speculation. When data is ambiguous, the imagination rushes in to populate the void with possibilities. The scientific method demands we choose the simplest explanation that fits all the data. For virtually every scientist studying 3 Atlas, that is a somewhat unusual comet. But human nature and the compelling allure of a grander story often prefers the more elaborate, more dramatic tale, especially one where humanity might be facing a celestial secret. We want 3 Atlas to be special because that makes our moment in history special. To be alive when humanity first encounters not just an interstellar rock, but an interstellar phenomenon, a shattered world, or a dark matter clump, is to live in an epoch of profound discovery. The reality is likely more modest, but no less significant. We are witnessing the universe's material mixing on a galactic scale. We are sampling the building blocks of other solar systems. That is extraordinary enough. But if the object itself isn't a hidden wrecking ball, could its passage have left other, subtler fingerprints on our technology, fingerprints that official sources might be quietly studying? This leads us to the evidence that is hardest to verify and easiest to doubt. The telemetry from our robotic scouts already deep in the void. Beyond the orbits of the planets, in the profound and empty dark, humanity's robotic avatars continue their endless journeys. Voyager 1 and 2, now in interstellar space. New Horizons, cruising through the Kuiper Belt. A handful of other probes, scattered like lonely watchmen, their instruments passively recording the solar wind, cosmic rays, and the faint magnetic fields of deep space. These spacecraft are marvels of navigation. Their positions are known with astonishing precision, tracked by the global network of the Deep Space Network, DSN. By measuring the Doppler shift in the constant two-way radio chatter between Earth and probe, engineers can determine a spacecraft's velocity down to fractions of a millimeter per second. Over time, this builds a trajectory map of incredible fidelity. This precision is what makes the next set of claims so intriguing and so fraught. In the months following the passage of 3 Atlas, a specific community of amateur analysts and independent researchers began dissecting publicly available tracking data from these deep space missions. These are individuals skilled in orbital mechanics, often with backgrounds in software or engineering, who dedicate time to sifting through the terabytes of mission data NASA and ESA released to the public. What they claimed to find were anomalies, not dramatic course changes, but subtle, residual accelerations, tiny pushes or pulls on the spacecraft that couldn't be explained by the known forces in their environment. Solar radiation pressure, the tiny thrust from outgassing or minor fuel leaks, the gravitational pull of known bodies. The most famous precedent is the Pioneer anomaly. For decades, the Pioneer 10 and 11 probes seem to be experiencing a tiny, unexplained sunward acceleration. It became a great mystery, a potential hint of new physics. After years of painstaking work, the culprit was found to be something profoundly mundane: thermal radiation. Heat, radiating unevenly from the spacecraft's power sources, was acting as a tiny thruster. The mystery was solved not by revolutionizing physics, but by meticulous accounting. The amateur analysts suggested that 3 Atlas might have created a new, similar anomaly. If the object possessed significant hidden mass, its gravitational field, as it passed through specific regions of the outer solar system, could have given a tiny, unplanned tug to a passing spacecraft like New Horizons or one of the Voyagers. The predicted effect would be a brief deviation in the Doppler data, a wiggle in the velocity curve that correlated in time with the object's position relative to the probe. Some forum posts contain graphs with circled glitches in the public trajectory data, claiming these wiggles match the timing of 3 Atlas's passage through the ecliptic plane or its closest approach to the Sun. The official position from the mission control teams was, and remains, silence. No press releases have announced unexplained accelerations linked to an interstellar visitor. No peer-reviewed papers have been published on the subject. When anomalies in spacecraft tracking do occur, and they do, they are attributed to the routine, complex business of managing aging machines billions of kilometers away. A thruster valve might seep a microscopic amount of propellant. A piece of multilayer insulation might tear and create a slight new solar sail effect. The DSN antennas themselves are subject to interference from Earth's atmosphere and solar weather, which can corrupt the pristine Doppler signal. All of this is normal, noisy, and well understood by the teams who live with the data daily. The absence of official commentary is, for the conspiracy-inclined, evidence in itself. They argue that raw telemetry is proprietary, that the data released to the public is smoothed, processed, and cleaned of such anomalies. If there were subtle, unexplained tugs that didn't fit existing models, would space agencies shout it from the rooftops? Or would they investigate quietly, internally, to understand it before making a statement that could cause public alarm or invite scientific controversy? The latter seems more prudent, and this very prudence fuels the speculation. Maybe the anomalies are real, and maybe they're being studied behind closed doors, a secret known only to a cadre of orbital navigators and astrophysicists. But let's consider the physical plausibility. For 3 Atlas to cause a detectable gravitational perturbation on a spacecraft, even a tiny one, the numbers once again rebel. Gravitational acceleration falls off with the square of the distance. The spacecraft are themselves in the overwhelming gravitational grip of the Sun. For a comet-mass object to produce a tug distinguishable from the solar background noise, it would need to pass extraordinarily close to the spacecraft, within tens of thousands of kilometers. The chances of such a close pass with any one of the handful of probes in the outer system are astronomically small. Alternatively, the object would need to be planetary in mass. We are back to the same impossible requirement. There's also the question of space-time curvature. General relativity predicts that massive objects warp the fabric of space-time. Could a spacecraft detect this warping through anomalies in the timing of its radio signals, even if its trajectory was unaffected? The travel time of a radio signal from Earth to a probe and back is known with incredible precision. If the signal passed through a region of space warped by 3 Atlas's gravity, its travel time might be minutely delayed or advanced, an effect known as a Shapiro time delay. But for an object of comet-scale mass, this delay would be measured in picoseconds, trillionths of a second, far, far below the detection threshold of the DSN's timing systems. The effect would be swamped by noise from the solar plasma itself. The most likely explanation for any claimed telemetry anomalies is, yet again, instrumental or environmental. These spacecraft are decades old, operating in the most hostile environment imaginable. Components degrade in unpredictable ways. The public data sets, while vast, are not always accompanied by the full context of spacecraft housekeeping data, internal temperatures, power levels, thruster performance, that engineers use to diagnose problems. Anomalies are the norm in deep space exploration. Attributing them to known causes is a full-time job. The human brain, however, is a pattern-matching engine, and when primed with the idea of a massive hidden interloper, it will find ways to match noise to that pattern. Confirmation bias ensures that data points which seem to fit are highlighted, while the vast sea of normal data is ignored. So, we are left with claims in the realm of unverified speculation. Extraordinary claims require extraordinary evidence. A few annotated graphs on an internet forum, without access to raw telemetry, and without the rigorous peer review process that filters out systematic error and bias, do not constitute such evidence. They are rumors, intriguing rumors that weave neatly into the larger tapestry of the Three Atlas mystery, but rumors nonetheless. Yet the persistence of these rumors points to a deeper tension, not in the data, but in the scientific community's communication. For while the public-facing message is one of uniform calm, there are in fact disagreements happening behind the scenes. Not about whether 3 Atlas is a threat, the consensus there is solid, but about how to model such objects, how to account for uncertainty, and where the line lies between responsible speculation and reckless sensationalism. This quiet tension is most evident in the world of those who map the future of the heavens, the ephemeris labs. The precise future positions of the planets are not guesses, they are calculated. This is the work of ephemeris labs, specialized groups at NASA's Jet Propulsion Laboratory, the European Space Agency, the Russian Institute of Applied Astronomy, and a handful of others. They maintain the digital oracles of celestial mechanics. Using supercomputers, they integrate the equations of motion for every significant body in the solar system, accounting for general relativistic effects, the pull of the largest asteroids, even the pressure of sunlight on small objects. The output is a series of numbers, an ephemeris, that tells you where Mars will be on a specific date in 2050, or where Jupiter will be in 2200. This work is the bedrock of space exploration, satellite navigation, and fundamental astronomy. It is the definition of authoritative prediction. When 3 Atlas entered the scene, these labs faced a quiet, procedural question. Should it be included in the long-term solar system models? The answer, for the mainstream institutions, was a swift and simple no. Its estimated mass was many orders of magnitude too small to affect the planets in any measurable way, even over millennia. Including, it would be a waste of computational resources, adding numerical noise without improving accuracy. The official ephemerides continued to be generated as if the interstellar visitor had never existed. The message was clear. 3 Atlas changes nothing. But in smaller, often privately funded or academic research groups, a different philosophy took hold. These are the sensitivity analysts, the what-if modelers. For them, 3 Atlas was a perfect test case, a real object with poorly constrained parameters. They deliberately pushed those parameters to their physical limits, not to predict, but to explore. What is the solar system's tolerance for error? How massive would an interloper need to be to produce observable effects in 10 years, 50 years, a century? They ran simulations not with the best fit comet mass, but with masses inflated by factors of 10, 100, 1000. They weren't claiming these were real. They were mapping the landscape of possibility. And the landscape, when viewed through this lens, was apocalyptic. Their simulations, as we've seen, showed Mercury destabilizing, Earth's climate shifting, orbits unraveling. This work, when stripped of its careful sensitivity analysis context and shared on public forums, became the proof of the wrecking ball hypothesis. The disagreement between the mainstream labs and the fringe modelers wasn't about physics. Both used Newton and Einstein. It was about intent. One group modeled reality, the other modeled the boundaries of plausibility. This confusion taps into a fundamental source of modern angst, cosmic anxiety. For most of history, the heavens were a placid backdrop, a clockwork of stars and planets that provided order and predictability. the telescope and physics revealed a more violent reality. Exploding stars, colliding galaxies, rogue asteroids. But these were distant, abstract threats. 3 Atlas made the threat personal and proximate. It was an intruder in our home, a tangible piece of the galaxy's chaos delivered to our doorstep. Its anomalous data created a vacuum of understanding, and into that vacuum rushed our oldest fears, dressed in the language of modern science. The axis tilt and climate reversal models are a perfect example. Earth's climate stability is the foundation of civilization. The idea that it could be rewritten, not by our own pollution, but by a gravitational nudge from a passing rock, is a specific type of horror. It combines the visceral fear of environmental collapse with the helplessness of a cosmic accident. It's fate, not fault. This narrative is psychologically potent. It absolves us of guilt for our planetary mismanagement and replaces it with a grand tragic destiny. Similarly, the Artemis Protocol leak, the rumor of a secret plan to use lunar bases as lifeboats, transforms humanity's expansive, exploratory goals into a desperate, hidden scramble for survival. It confirms every suspicion about government secrecy and elite self-preservation. It makes sense of the accelerating space race in a darkly satisfying way. They're not trying to explore, they're trying to escape. This is the psychological engine driving the entire 3 Atlas phenomenon. Apophenia, the tendency to perceive meaningful connections between unrelated things. The megaquake, the internet glitch, the solar flares, the orbital simulations, all were real events. Their coincidence in time with 3 Atlas's passage was just that, a coincidence. But the human brain is wired to reject coincidence as an explanation. We are storytellers. We need narrative, a single, mysterious cause that links disparate, frightening events is cognitively preferable to the chaos of random chance. 3 Atlas became the protagonist in a story we are unconsciously writing about a dangerous, interconnected cosmos. The vacuum decay scare of early 2025, though unrelated to 3 Atlas, operated on the same psychological circuitry. A tentative, ambiguous result from a particle collider was transformed by media and social networks into a credible threat of universal annihilation. The correction never travels as fast or as far as the original scare. This dynamic erodes trust in scientific institutions, creating a vicious cycle. Scientists, burned by sensationalism, become more cautious and opaque in their communication. This opacity fuels public mistrust and the belief that they are hiding something, which in turn makes the next sensational claim more believable. 3 Atlas sits at the heart of this cycle. The calm, repeated assurances from official bodies are, to a growing segment of the public, evidence not of safety, but of a cover-up. What does this tell us about our moment in history? 2025 may be remembered less for the discovery of 3 Atlas itself, and more for what that discovery revealed about us. We are a species that has developed the tools to detect interstellar visitors, to model solar system chaos, to probe the fundamental stability of the vacuum. But we have not yet developed the emotional or cognitive maturity to process what these tools tell us without retreating into primal fear and conspiratorial narrative. We possess godlike instruments, but are governed by ancient limbic brains. The universe revealed by our technology is vast, dynamic, and indifferent. Our psyches crave a universe that is knowable, stable, and meaningful. The collision between these two realities generates cosmic anxiety, and 3 Atlas became its perfect symbol. The object's legacy, therefore, is dual. Scientifically, it is a milestone, a chemically peculiar interstellar comet that expands our knowledge of galactic material. Culturally and psychologically, It is a Rorschach test. It shows our readiness to see portents in the sky, our vulnerability to narratives of hidden danger, and our deep, unresolved tension between the power of our knowledge and the terror of what that knowledge might eventually contain. The real question posed by 3 Atlas is not, are we in danger, but how will we choose to live in a universe that is finally, undeniably, and magnificently not about us? The next visitor will come. Whether it brings knowledge or fear will depend less on its composition and more on our own. The silence was an illusion. For generations we gazed at the static, jeweled tapestry of the night sky and imagined a cosmic quiet broken only by the gentle, predictable rhythms of our local planets. The discovery of 3 Atlas and the events that swirled in its narrative wake shattered that illusion forever. 2025 will be remembered as the year the universe grew loud, not with sound, but with presence, with activity, with a relentless dynamic complexity that insists on our attention. It was the year we truly internalized that our solar system is not a sealed garden, but a porous clearing in an endless, flowing galactic forest. Things pass through. Some are harmless snowballs. Some might be something else. And we are only beginning to learn how to tell the difference. The scientific harvest from 3 Atlas alone was profound. The James Webb Space Telescope's spectroscopic data provided a chemical portrait of another star's building blocks. The dominance of carbon dioxide over water ice rewrote assumptions about comet formation in other systems. The hints of complex organics and processed metals spoke of a violent, varied galactic history, where planetary material is forged, shattered, and scattered across the light years. Each data point was a message in a bottle from a place we will never visit, telling us that the recipes for making worlds are more diverse than our own solar system led us to believe. This alone is a revolutionary, humbling realization. We are not the template, we are a single data point. Technologically, 2025 was a year of paradoxical leaps. We developed AI capable of predicting the sun's violent outbursts, a tool of immense practical power that also centralizes control and risk. We deployed quantum gravimeters so sensitive they can hear the faint whisper of underground water, and in their exquisite sensitivity, we imagined they heard the footsteps of passing dark matter. Our global network, the Internet, proved to be both astonishingly robust and frighteningly fragile, a system so complex that its failures mimic the signatures of cosmic events. We live in a world where our machines are now sensitive enough to theoretically tremble at the cosmos, even if they mostly tremble at our own bugs. Psychologically, we faced a series of stress tests. The 3 Atlas saga, the vacuum decay scare, the megaquake warnings. They were drills for a new kind of existential anxiety. We practiced being afraid of things beyond our atmosphere, beyond our control. The media ecosystems and social networks that shape our collective consciousness proved themselves brilliantly adapted for amplifying this fear, and terribly maladapted for managing it with nuance or truth. We saw how quickly frontier science can morph into apocalyptic folklore, and how difficult it is to put that folklore back in the bottle. So, what is the final synthesized truth about 3 Atlas? After 10 parts of investigation, chasing leads from gravitational theory to seismic data, from network logs to orbital simulations, a clear picture emerges from the noise. 3 Atlas was an interstellar comet. It was unusual, fascinating, scientifically precious. It was not a gravitational wrecking ball. Its mass was minuscule. It did not trigger earthquakes, warp internet time, or stir the sun to fury. The terrifying orbital chaos scenarios require physics-breaking assumptions contradicted by every reliable observation. The connections were coincidences, woven into narrative by our powerful, pattern-seeking minds in an age of profound cosmic anxiety. But to dismiss the entire episode as a false alarm is to miss its monumental significance. The false alarm is the signal. The fact that a passing comet could generate such a sprawling, multi-continent, multidiscipline cascade of speculation, fear, and investigation is a symptom of a new human condition. We have become aware of our cosmic vulnerability. For all of history, existential threats were local: plague, famine, war, natural disaster. Now we can realistically conceive of threats that are planetary, solar, even universal in scale. Our imagination has been outpaced by our physics. 3 Atlas was the first tangible peg on which to hang this new, formless dread. Looking forward, the legacy of 2025 and 3 Atlas must be one of preparation, not paranoia. It highlighted critical gaps. Our planetary defense networks are tuned for asteroids from within our system, not for fast, hyperbolic intruders from outside it. We need better, faster all-sky surveys to catch the next 3 Atlas earlier, giving us time not for panic, but for study. Our scientific communication systems are broken, failing to translate uncertainty and nuance to a public hungry for certainty and drama. This must be fixed, not just for cosmic threats, but for climate science, pandemic response, and all complex challenges. The Artemis Protocol is a fiction, but the impulse behind it is logical. Becoming a multi-planet species is not about escaping a doomed Earth. It is about ensuring the long-term survival of life and consciousness. 3 Atlas reminds us that planets are fragile, temporary habitats in a dynamic universe. Spreading out is the ultimate insurance policy, not against a specific comet, but against the inevitable statistics of cosmic events over geological time. The clock is not ticking down to a 50-year ejection, but a different clock is ticking, the clock of human maturity. We've been given a glimpse of the true nature of our galactic neighborhood. It is not a quiet suburb. It is a wilderness, beautiful and dangerous, full of wonders and potential hazards. We can respond to this knowledge with fear, building digital fortresses of conspiracy and despair. Or we can respond with courage, curiosity, and a renewed commitment to rationality. We can choose to see 3 Atlas not as a harbinger of doom, but as a wake-up call. A call to invest in science, to build resilient systems, to improve our collective discernment, and to step into the cosmos not as fearful children, but as aware, responsible adults. The next visitor will come. It might be a snowball, a rubble pile, or something beyond our current imagination. When it does, will we have learned from 3 Atlas? Will we meet it with telescopes and spectrometers, or with social media panic and apocalyptic fantasies? The answer to that question will determine not our survival, but our worthiness as a species taking its first tentative steps onto the galactic stage. The universe has grown loud. The question now is, how will we choose to listen?